You think nature is playing fair? Look at the tree, any tree, the one outside your window, the oak in the park, the pine on the mountain. Look at how it branches. The trunk splits into large limbs. Those limbs split into smaller branches. Those branches split into twigs. The twigs split into even smaller twigs. And at the end, leaves, thousands of them, millions of them, all connected to that single trunk through this impossibly intricate network of branching. Now here's the question no one asks. Why does it look like that? Why that particular pattern? Why do branches split and split and split again in that specific way? Most people shrug. That's just how trees grow. Nature designed them that way. It's beautiful, it's organic, it's natural. But that's not an answer. That's just describing what you see. When you really ask why trees branch the way they do, when you dig into the mathematics behind that pattern, you discover something that changes everything you think you know about how nature builds things. Nature isn't playing fair. Nature is cheating. And once you understand the cheat, you see it everywhere. Let me show you what I mean. Start with a problem. You're a tree. You need to do two things. First, you need to collect sunlight, lots of it. Sunlight is your energy source. Without it, you die. Second, you need to transport water and nutrients from your roots to every single leaf. Thousands of leaves, millions of leaves. Each one needs water, each one needs minerals, each one is a tiny factory that needs a constant supply. So you have a transportation problem. You need to build a network that reaches every leaf while using as little material as possible. Wood is expensive. It takes energy to grow. You can't waste it. Here's where it gets interesting. If you were an engineer, you might try to solve this problem with straight lines, efficient pipes, direct routes. That's how we build things. Water mains, electrical grids, highway systems. We love straight lines. We love efficiency at a single scale. But trees don't do that. Trees branch. They split and subdivide over and over. Why? Because trees aren't solving a single scale problem, they're solving a multi-scale problem, and that changes everything. Think about what a tree actually needs to accomplish. It needs to fill a three-dimensional volume with leaves, not just cover an area, fill a volume, because sunlight comes from above, from the sides, at different angles throughout the day. A tree that only spread leaves in one plane would waste most of that light. So the tree needs to occupy space. It needs to be a three-dimensional structure. But here's the constraint. The tree is fed from a single point, the root system connecting to the trunk. Everything flows through that one trunk. Every drop of water, every mineral, every bit of sugar flowing back down. One trunk serving millions of endpoints. Now think about the mathematics of this. If you have a single source and millions of destinations spread through a three-dimensional volume, what's the most efficient network? What shape minimizes the total length of pipe while reaching every destination? The answer is branching. Hierarchical branching, splitting over and over at regular ratios. And here's the beautiful part. The splitting isn't random. It follows rules, scaling rules. When a branch splits, the daughter branches are smaller than the parent, not randomly smaller, precisely smaller. The ratio of diameters follows a mathematical law. The angles of splitting follow patterns. The lengths of successive branches follow ratios. This is what I call a scaling law, a rule that describes how properties change as you move from one scale to another. In trees, the cross-sectional area of the trunk equals the sum of the cross-sectional areas of all the branches above it. This is called the pipe model. It's as if the trunk contains all the pipes that will eventually become separate branches bundled together. When the trunk splits, those pipes separate. But the total carrying capacity stays the same. This principle applies at every level, every branch point, every split, the same ratio, the same rule, scale after scale after scale. And this is why I say nature is cheating. Classical science, classical engineering, classical thinking loves single scales. We analyze things at one magnification. We optimize for one size. We think in terms of fixed dimensions. But trees don't work that way. Trees work across scales. They use the same trick at every level of magnification. The pattern of branching you see in the trunk repeats in miniature in every branch, every twig, every vein, in every leaf. This is self-similarity. Not exact self-similarity. The branches aren't perfect miniature copies of the whole tree, but approximate self-similarity. Similar enough that the same mathematical rules apply at every scale. When you see this, when you really see it, you realize that the tree isn't solving millions of separate problems. It's solving one problem and then repeating the solution at every scale. That's the cheat. That's the trick. Nature found one good design and used it over and over, scaling it up and down as needed. Let me make this concrete. Look at the leaf. Look at the veins in that leaf. What do you see? Branching, the main vein splits into smaller veins. Those split into smaller veins still. The pattern looks like a miniature tree because it's solving the same problem at a smaller scale. Transport from one source to many destinations spread through a surface. Now look at your lungs, your bronchial tree. The trachea splits into bronchi. Those split into smaller bronchi. Those split into bronchioles over and over, about 23 levels of branching until you reach the alveoli, the tiny air sacs where oxygen actually enters your blood. Why this structure? Same reason as the tree. You need to fill a volume. You need to maximize surface area for gas exchange. You need to reach every part of the lung from a single source. The solution? Branching. Hierarchical self-similar branching. Look at your circulatory system. Your heart pumps blood into the aorta. The aorta branches into arteries. Arteries branch into smaller arteries. Those branch into arterioles. Those branch into capillaries. Millions of capillaries reaching every cell in your body. Then the blood returns through venules, veins, larger veins back to the heart. Same pattern, same scaling law, same cheat. Look at river systems. A main river fed by tributaries. Those tributaries fed by smaller streams. Those streams fed by smaller creeks. Those creeks fed by runoff from the land. The pattern of a river basin seen from above looks like a tree turned upside down because it's solving the inverse problem, collecting water from an area and funneling it to a single point. Same mathematics, same scaling rules, same branching structure. This is not coincidence. This is not design in the sense of someone planning it. This is the inevitable solution to a certain class of problems. When you need to connect a single point to many points distributed through space, when you need to do it efficiently, when you need to minimize material while maximizing coverage, you get branching, you get a hierarchical structure, you get self-similarity across scales. Nature discovered this not through intelligence, but through selection. Organisms that used this pattern survived. Organisms that didn't, over billions of years, the same solution was rediscovered over and over because it's the right solution. But here's what classical science missed. Classical science looked at these structures and described them. Oak trees branch like this, maple trees branch like that, lungs have this many levels of branching, rivers follow these patterns. What classical science didn't do was see the underlying unity. The same mathematics, the same scaling laws, the same geometric principle appearing in completely different systems. I saw it in the 1960s and 70s when I started studying what I called fractals. I noticed something remarkable. The mathematics of irregular shapes, the geometry of roughness kept appearing in system after system. Coastlines, mountains, clouds, turbulence, and yes, trees. Trees are fractals, not perfect mathematical fractals, but natural fractals. They exhibit approximate self-similarity across scales. The branching pattern at large scales resembles the branching pattern at small scales, not identical, but similar enough that the same mathematical description applies. This is what makes fractal geometry powerful. It's not just a way to draw pretty pictures, it's a language for describing structures that classical geometry couldn't handle. Classical geometry deals with smooth shapes, exact circles, spheres, planes, cones, shapes defined by their dimension, one-dimensional lines, two-dimensional surfaces, three-dimensional volumes. But trees aren't smooth, their surfaces are rough, their structures are branched and irregular, and they don't fit neatly into integer dimensions. A tree's branching structure is more than one-dimensional, but less than three-dimensional. It's somewhere in between. It has a fractional dimension, a fractal dimension that captures how it fills space. This isn't just mathematical abstraction. The fractal dimension of a tree tells you something real about how it functions. It tells you how efficiently it fills space with leaves. It tells you how its surface area scales with its volume. It tells you about its transport properties. When you measure a tree's fractal dimension, you're measuring a fundamental property of its design. And remarkably, trees of the same species tend to have similar fractal dimensions. The branching pattern, the scaling law, is encoded in the tree's genes. It's part of what makes an oak and a maple a maple. Now here's the deeper insight. Why does this matter? Why should you care that trees follow scaling laws? Because it changes how you understand complexity. For most of history, complexity was mysterious. Complex things were assumed to require complex explanations. A tree is complex, therefore its design must be elaborate, intricate, requiring detailed specifications for every branch and twig. But that's wrong. A tree is complex in its appearance, but simple in its rules. The complexity emerges from the repeated application of simple scaling rules across many levels. You don't need to specify where every branch goes. You need to specify the branching rules. How daughter branches relate to parent branches in size, angle, length. Apply those rules repeatedly, and the complex structure emerges automatically. This is the secret of natural complexity. It's not designed from the top down with every detail specified. It's generated from the bottom up with simple rules applied recursively. A tree doesn't have a blueprint showing the location of every twig. It has an algorithm, a set of growth rules that generate twigs as needed. The rules are simple. The result is complex. This insight extends far beyond trees. Your brain has roughly 86 billion neurons connected by trillions of synapses. Is every connection specified in your DNA? No. Your DNA doesn't have enough information to specify trillions of connections. Instead, your brain develops through growth rules. Neurons extend axons following chemical gradients. Connections form based on activity patterns. Simple rules repeated billions of times generate astronomical complexity. Economies are complex systems, millions of people making billions of decisions. Is there a central plan specifying every transaction? No. Simple rules of supply and demand repeated across countless interactions generate complex market dynamics. Cities are complex systems. Buildings, roads, neighborhoods, all interconnected. No one designs a city from scratch with every building specified. Cities grow through repeated application of zoning rules, building codes, economic incentives, simple rules, complex results. This is the pattern. Complexity emerges from simplicity through repetition across scales. And trees are the perfect example, the perfect demonstration of how nature generates intricate structure from elementary rules. When you look at a tree and see complexity, you're seeing an illusion. The complexity isn't in the specification, it's in the iteration. The tree followed simple rules many times and complexity emerged. This is what I mean when I say nature cheats. Nature doesn't solve complex problems with complex solutions. Nature finds simple solutions and applies them recursively. The same trick at every scale. We humans, with our love of straight lines and optimal solutions at single scales, look at the result and see chaos, randomness, inexplicable intricacy. We think nature must be doing something complicated. We think there must be some elaborate design principle we're missing. There isn't. The principle is simple. Repeat the same pattern at every scale. Let the complexity take care of itself. This is why fractal thinking matters. It's not just a branch of mathematics, it's a way of seeing, a way of understanding how complex structures arise in nature. When I developed fractal geometry, I wasn't trying to create abstract art or mathematical curiosities. I was trying to understand the real world, the rough world, the world of mountains and clouds and coastlines and trees, the world that classical mathematics couldn't describe. And I found that the key to understanding this world was scale, not analyzing things at one fixed scale, but understanding how properties change across scales, not looking for smoothness, but embracing roughness, not seeking single optimal solutions, but recognizing hierarchical self-similar structures. Trees taught me this. Trees and rivers and lungs and lightning bolts and 100 other natural phenomena that all exhibited the same pattern. The pattern is branching. The mathematics is scaling laws. The geometry is fractal, and once you see it, you can't unsee it. Look at a tree now. What do you see? You see a solution to a transportation problem. You see a network that connects one source to millions of destinations. You see a structure that fills three-dimensional space efficiently. But more than that, you see a scaling law in action. You see the same pattern repeated at every level of magnification. You see self-similarity across scales. You see nature's cheat code. The tree didn't need to figure out where every branch should go. It just needed to follow the rules. Split at this ratio, branch at this angle, repeat until you reach the leaves. Simple rules, complex results. This is how nature builds things, not through elaborate design, but through recursive application of scaling laws. Not through optimization at a single scale, but through strategies that work across all scales. The next time someone asks why trees look the way they do, you can tell them, trees branch because branching is the solution to multi-scale transport problems. The pattern repeats because self-similar structures are efficient across scales. The complexity emerges because simple rules applied recursively generate intricate results. Nature isn't cheating in the sense of breaking rules. Nature is cheating in the sense of using one trick over and over, finding what works and scaling it. Using the same pattern at every level. We call it cheating because it seems too simple. It seems like there should be more to it. We want elaborate explanations for elaborate phenomena. But nature doesn't care what we want. Nature does what works. And what works is scaling laws. What works is self-similarity. What works is fractal structure. The trees knew this long before we did. They've been practicing fractal geometry for 400 million years. We're just beginning to understand. And that understanding changes everything, not just how we see trees, how we see complexity itself, how we see the relationship between a simple rule and intricate outcomes. How we see the role of scale in shaping the natural world. Classical geometry gave us tools for smooth shapes. A fractal geometry gives us tools for rough shapes. Classical thinking focused on single scales. Fractal thinking embraces all scales. Classical science sought complex explanations for complex phenomena. Fractal science reveals simple rules generating complexity. Trees stand as proof. 400 million years of proof that nature's solutions are elegant, not because they're complicated, but because they're recursive. Not because they're optimal at one scale, but because they work at every scale. Nature cheats. And the cheat is beautiful. Not comfort, not simplicity, truth. You think the Mandelbrot set is just a picture, a pretty image you've seen 1,000 times. Psychedelic colors, no? Spirals within spirals. Maybe you had it as a screensaver in the 90s. Maybe you saw it in a documentary about chaos or fractals. Beautiful, mysterious, something mathematicians made with computers. Fine. But what is it really? What are you actually looking at when you see that famous black shape with its bulbs and tendrils and this infinite coastline? Most people have never really thought about this. They see the image and think, fractals, infinite detail, the same pattern repeating forever, again, and they move on. But that's not an answer. That's just repeating words you've heard somewhere. When you really ask what the Mandelbrot set is, when you dig into why the zoom never ends, you discover something so strange, so fundamentally different from anything else in mathematics that it changes how you see structure itself. The Mandelbrot set isn't a picture. It's not an image someone drew or rendered. It's not stored anywhere. It's a mathematical process that generates structure at every scale you care to look. And here's the part that should break your intuition. The deeper you zoom, the more structure appears, not less. More. New structure. structure that wasn't visible before, structure that couldn't have been predicted from what you saw at larger scales. Let me show you what I mean. Start with the simplest possible thing, a rule, one rule. Take a number, square it, add another number. That's it. Z goes to Z, squared plus C. The most elementary operation you can imagine. Squaring and adding. A child can understand it. Now here's the question. You pick a number C, any complex number on the plane, you start with Z equals 0. You apply the rule. Z becomes C, you apply it again, Z becomes C squared plus C, again and again and again and again. Why? What happens? For some values of C, the numbers stay small. They bounce around near 0 forever. Bounded, contained, stable. For other values of C, the numbers explode. They grow larger and larger without limit. They escape to infinity. The Mandelbrot set is simply the collection of all those C values where the numbers don't escape. The black region, the points that stay bounded forever under iteration. That's it. That's the entire definition. One rule, iterate, check if it escapes or not, color it accordingly. Now stop and think about what just happened. We didn't draw anything. We didn't design anything. We didn't specify any spirals or bulbs or tendrils. Or we just asked the question, for which points does this simple process stay bounded? And out of that question, purely from that question, emerges this impossibly intricate shape. Bulbs attached to bulbs the sauce that spin into other spirals, filaments so thin they seem one-dimensional, yet zoom in and they bloom into full two-dimensional complexity. Seahorses, elephants, lightning bolts, an entire zoo of forms, none of which we specified, all of which emerged from one rule. This is what people miss when they call it a picture. A picture is something you create. You decide what goes where. You choose the shapes. The Mandelbrot set isn't created. It's discovered. It was always there, implicit in the rule, waiting for someone to look. But here's where it gets stranger. You've probably heard that fractals are self-similar. The same pattern repeats at every scale. Zoom in and you see smaller copies of the whole. This is true for simple fractals. The Sierpinski triangle, the Koch snowflake, zoom in. Exact copies appear. The Mandelbrot set doesn't work like that. And this is crucial. When you zoom into the Mandelbrot set, you don't see exact copies. You see approximate copies, near self-similarity, not exact self-similarity. You encounter baby Mandelbrots, yes, tiny versions of the whole set embedded within it. But each one is slightly different, surrounded by different spiral structures, connected by different filaments, living in a different neighborhood that colors its character. Think about what this means. At every scale, there's something familiar. You recognize the shape, you've seen it before, but at every scale, there's also something new. Details you couldn't have predicted, variations you've never encountered. The set quotes itself, but never repeats itself. This is why the zoom never ends. If the Mandelbrot set were exactly self-similar, zooming would eventually become boring. You'd see the same thing again and again. But because it's only approximately self-similar, every zoom reveals new structure, new arrangements of old themes, familiar motifs in unfamiliar configurations. It's like a symphony that uses the same instruments, but never plays the same melody twice. Let me make this concrete. Pick a point on on the boundary of the Mandelbrot set. The boundary is where everything interesting happens. Inside the set, points are stable. Outside the set, points escape. But on the boundary, you're right at the edge. The tiniest change in position can flip a point from stable to escaping. Now zoom in on that boundary point. What do you see? You see the boundary getting more complex, not simpler. You see filigree, you see spirals nested within spirals. You see the edge becoming more and more intricate the closer you look. In ordinary geometry, when you zoom in on a curve, it gets simpler. A circle magnified enough looks like a straight line. A coastline zoomed in enough becomes individual grains of sand. Smoothness emerges from roughness at small scales. The Mandelbrot set does the opposite. Zoom in and it gets more complex, always, without limit. There is no smallest scale at which the boundary becomes smooth. There is no resolution at which you've seen everything. The complexity goes all the way down. Why? What's generating this infinite structure? The answer lies in what I call roughness, but not random roughness, structured roughness, roughness that follows rules. Think about iteration. You apply the rule once, twice, 1,000 times, 1,000,000 times. Each iteration adds information. Each iteration separates points that were close together. Points that looked identical at coarse resolution turn out to have completely different fates at fine resolution. Near the boundary, this separation is extreme. 2 points might be arbitrarily close, so close that no computer could distinguish them, yet one escapes to infinity and the other stays bounded forever. The iteration process magnifies these microscopic differences into macroscopic outcomes. This is sensitive dependence on initial conditions. The same phenomenon that makes weather prediction impossible beyond a few days. The same phenomenon that underlies chaos. But here, instead of making things unpredictable, it generates structure. Every time you zoom in, you're asking, among these points that looked similar before, which ones escape and which ones stay? The answer is never simple. The answer is always intricate because the iteration process has had time to separate them in complex ways. Here's another way to think about it. The Mandelbrot set exists at the intersection of order and chaos. Inside the set, behavior is orderly. Iterations stay bounded, often settling into periodic cycles. Outside the set, behavior is also orderly in its way. Iterations escape, growing without bound. But on the boundary, you're between these two regimes. You're in the zone where tiny changes produce dramatically different outcomes. This zone isn't thin, it isn't a simple curve, it's infinitely intricate, fractal, because the transition from bounded to unbounded is itself infinitely complex. Now you might ask, why should I care? Why does this matter? It's just mathematics, just abstract numbers and the rules. What does it have to do with reality? Everything. Look at nature. Really look. What do you see? Coastlines that look jagged at every scale. Not smooth curves that straighten when you zoom in, but irregular boundaries that reveal new irregularity the closer you look. Trees whose branches branch into smaller branches that branch into smaller branches still, each level of branching following similar but not identical patterns. Mountains whose surfaces are rough at every scale. Zoom in with a microscope and the roughness doesn't disappear. It transforms into different roughness. Clouds, lightning bolts, blood vessels, river networks, the distribution of galaxies in the universe. None of these follow the rules of classical geometry. Classical geometry deals with smooth shapes, circles, spheres, planes, shapes that would simplify when you zoom in, shapes characterized by their dimension, one-dimensional lines, two-dimensional surfaces, three-dimensional volumes. But natural shapes don't simplify when you zoom in. They maintain their complexity across scales. They have structure at every level of magnification. And they often fall between dimensions, not quite one-dimensional, not quite two-dimensional, something in between. Fractal, the Mandelbrot set, taught me this, not because it describes any particular natural phenomenon, but because it shows that simple rules can generate infinite complexity. That iteration, recursion, feedback can create structure at every scale without limit. Before I studied these objects, most scientists assumed that simple rules produce simple outcomes. You want complex behavior, you need the complex rules, you want rich structure, you need elaborate mechanisms. The Mandelbrot set demolishes this assumption. One rule, z goes to z squared plus c. Apply it repeatedly. Out comes infinite complexity. The rule couldn't be simpler. The outcome couldn't be richer. This principle extends far beyond pure mathematics. Think about how markets behave. Fluctuations at every time scale. Daily movements that look like monthly movements, that look like yearly movements. Self-similar, but not identical. Infinite intricacy emerging from the interaction of many simple decisions. Think about how turbulence works. A smooth flow becomes unstable, breaks into eddies, eddies within eddies, structure at every scale down to molecular dissipation. Simple fluid equations producing infinite complexity. Think about how languages evolve, how cultures develop, how ecosystems arrange themselves. Pattern within pattern, scale within scale, complexity emerging from simplicity through iteration and feedback. This is what I spent my life trying to understand, not specific applications, but the underlying principle, the mathematics of roughness, the geometry of the irregular, the science of complexity. And the Mandelbrot set is the purest example, a window into how simple iteration generates infinite structure. Let me tell you something that still amazes me. When I first plotted the Mandelbrot set on a computer in the late 1970s, I didn't know what I would see. I'd studied similar mathematical objects, I had conjectures, but I didn't expect this. I remember zooming in for the first time, seeing the boundary get more complex instead of simpler, finding baby Mandelbrots in unexpected places, discovering spiral structures that seemed to have no end. I zoomed deeper and deeper. Every level revealed new forms. Every magnification brought new surprises. The set seemed alive, generative, creative in a way mathematics rarely is. And here's the key point. I wasn't creating anything. I was discovering. The structure was already there and encoded in the simple rule. I was just the first to look. This is what makes mathematics so extraordinary. These objects don't depend on me, on humanity, on Earth, on the universe. The Mandelbrot set would exist even if no one ever discovered it. Its properties are eternal, unchanging, absolute. We access them through computation and proof, but we don't create them. When you zoom into the Mandelbrot set, you're not generating images. You're exploring a mathematical continent that exists outside of time and space. Every detail you find was always there. Every spiral, every bulb, every filament has been waiting since before the Big Bang for someone to look. Some people find this cold. Abstract mathematics removed from human concern. I find it the opposite. it the most direct connection we have to something beyond ourselves, something permanent, something true. Now back to the original question, why doesn't the zoom ever end? Because the Mandelbrot set encodes a process, not a thing. Every point you examine requires infinite iteration to determine its status. Does it escape or not? You can never know for certain by looking at finite iterations. You can only approximate. And because the boundaries were bounded and unbounded, points interleave in infinitely complex ways. No matter how closely you look, there's always more interleaving to discover, always more points to separate, always more structure to resolve. The zoom never ends because the process never terminates, because iteration goes on forever, because the question, does this point escape, has infinitely nuanced answers along the boundary. Here's the deepest thing. Classical geometry loves flat spaces. Euclidean geometry assumes that at small enough scales everything looks flat. Smooth, regular. This assumption underlies all of classical physics, classical engineering, classical mathematics, but the Mandelbrot set suggests a different possibility. What if structure persists at all scales? What if roughness never smooths out? What if complexity is fundamental, not derived? This would change everything about how we model the world. Instead of smooth approximations that break down at fine scales, we might need rough models that maintain their character across scales. Instead of dimension as a whole number, we might need fractional dimensions that capture the intrinsic complexity of natural shapes. I don't have all the answers. No one does. But I believe the Mandelbrot set points toward a new geometry, a geometry adequate to the rough, irregular, complex world we actually live in. Yeah? A geometry where infinite structure is the rule, not the exception. When you look at the Mandelbrot set, you're not looking at a picture. You're looking at a doorway into a mathematics that embraces complexity instead of fleeing from it. A doorway into a science that sees roughness as fundamental, not as noise to be averaged away. A doorway into a new way of understanding the endless structure of nature itself. The zoom never ends because the universe never simplifies. At every scale, there's more to see, more to understand, more to discover. The Mandelbrot set shows us that simple rules can generate this infinite richness. That complexity isn't the opposite of simplicity, but its offspring. That iteration, the most elementary of processes, can create worlds within worlds without limit, and that changes everything. Not comfort, not familiarity, truth. You think calm means safe. Look around you. The world seems stable. The sun rises every morning. The seasons cycle predictably. Your heart beats in a steady rhythm. The stock market, despite occasional bumps, trends upward over decades. Everything seems to follow patterns you can understand, predict, control, calm, stable, safe. It's a trap. The most dangerous thing you can do is mistake calm for understanding, mistake stability for permanence, mistake the absence of visible change for the absence of hidden forces building toward catastrophe. I spent my entire career studying systems that appear calm on the surface, but hide infinite complexity underneath. Systems where the peaceful center deceives you about the chaotic edges. Systems where everything looks stable right until the moment it isn't. And what I discovered changes everything you think you know about stability, chaos, and where the real action happens in nature and mathematics. Let me show you what I mean. Start with something simple. A pendulum, you push it, it swings back and forth, regular, predictable, the very definition of stable periodic motion. Scientists have studied pendulums for centuries. Newton used them. Galileo used them. They're the textbook example of orderly behavior. Now add a second pendulum, attach it to the end of the first one. A double pendulum, 2 arms, 2 pivots, same basic physics. Watch what happens. The motion becomes wild, unpredictable, chaotic in the technical sense. The double pendulum swings in patterns that never repeat. Tiny differences in starting position lead to completely different trajectories. You cannot predict where it will be 10 seconds from now, let alone 10 minutes. Same physics, same simple rules, but the system has crossed a threshold. It has moved from the calm interior of predictable behavior to the chaotic boundary where everything becomes sensitive and unpredictable. This is the first lesson. Calm is not a property of the universe. Calm is a property of where you're looking. The single pendulum seems calm because you're examining a simple system far from any threshold. Add one more degree of freedom, one more interaction, and suddenly you're at the edge. Suddenly calm dissolves into chaos. Now think about the Mandelbrot set, that famous fractalgeometry shape it spent years exploring. Inside the set, behavior is calm, iterations converge, numbers settle into stable patterns, periodic cycles, predictable outcomes. The interior is boring, mathematically speaking. Outside the set, behavior is also predictable in its way. Iterations explode to infinity. Numbers escape. The outcome is certain, just in the opposite direction, but the boundary, the edge between inside and outside, that's where everything interesting happens. That's where calm becomes chaos. That's where stability dissolves into infinite complexity. The boundary of the Mandelbrot set is not a line. It's a fractal dust of infinite intricacy. Points that stay bounded and points that escape are woven together so tightly that you can never separate them with finite precision. No matter how closely you look, you find more mixing, more complexity, more structure. This is not an accident. This is a fundamental truth about how systems behave. The center is calm because the center is far from any transition. The edge is chaotic because the edge is where different behaviors meet and compete. And here's the insight da necessaritat should restructure how you see the world. The interesting things, the important things, the things that determine how systems actually behave, they don't happen in the calm center. They happen at the chaotic edge. Let me make this concrete with examples from nature. Consider weather. Most of the time, weather is predictable enough. High pressure systems bring clear skies. Low pressure systems bring clouds and rain. The general patterns follow rules we understand, but sometimes weather becomes extreme. Hurricanes form, tornadoes touch down, heat waves persist for weeks, cold snaps, freeze everything. Where do these extreme events come from? They come from the boundaries, the fronts, the places where warm air meets cold air, where moist air meets dry air, where high pressure meets low pressure. The transitions, the edges. A hurricane forms when conditions are just right at the boundary between warm ocean water and cooler air above. The system is poised at a threshold. Small differences in temperature, humidity, and wind shear determine whether a hurricane forms or dissipates. The boundary region is exquisitely sensitive. The calm center of a high pressure system is boring. Nothing much happens there, but the edges of that system where it interacts with other air masses, that's where storms develop. That's where weather becomes interesting and dangerous. You can't understand weather by studying the calm centers. You have to understand the chaotic boundaries. Consider ecosystems. A mature forest seems stable. Trees grow slowly. Species populations fluctuate within ranges. The system persists for centuries. But look at the edges. The boundary between forest and grassland, the ecotone, as ecologists call it, that's where biodiversity peaks. That's where species from both ecosystems meet and interact. That's where new adaptations emerge. The interior of the forest is stable precisely because it's far from any transition. Everything has settled into equilibrium. But the edge is dynamic. The edge is where change happens. The edge is where the future of the ecosystem gets determined. When climate shifts, when conditions change, it's the edges that respond first. The boundaries move, the transitions relocate. The calm interior only changes after the edges have already transformed. Consider your own body. Your heart beats in a steady rhythm, calm, stable, predictable, but that's not quite true, is it? A perfectly regular heartbeat, one that never varies, is actually a sign of disease. Healthy hearts show variability, beat-to-beat fluctuations, subtle irregularities that indicate the heart is responsive and adaptable. Your heart is not operating in the calm center of its possible behaviors. It's operating near an edge, near enough to chaos that it can respond quickly to changing demands, near enough to stability that it doesn't collapse into arrhythmia. The healthiest state is not maximum stability. The healthiest state is poised at the boundary between order and chaos, ready to respond, capable of adaptation, not trapped in the rigidity of perfect calm. This pattern repeats everywhere I look. Financial markets. Most of the time, prices fluctuate within reasonable ranges. Volatility is contained. The system seems stable, but markets are not actually stable. They're poised at a critical threshold. They operate at the edge between orderly price discovery and chaotic panic. Most days, they stay on the orderly side, but the chaotic side is always there, always accessible, always threatening. When markets crash, they don't gradually become unstable. They flip suddenly from apparent calm to extreme chaos. The transition is abrupt because the system was never truly stable. It was always at the edge, always sensitive, always capable of catastrophic change. The calm you saw before the crash was an illusion. The system was operating in the boundary region where small perturbations could trigger large responses. The apparent stability was the trap. Tectonic plates. Most of the time, the ground beneath your feet seems perfectly stable, solid, reliable. You build cities on it. You assume it will always be there, but the plates are moving slowly, imperceptibly. They're grinding against each other. Stress is building. The system is accumulating energy that must eventually be released, and then suddenly an earthquake. The ground that seemed so stable lurches violently. Buildings collapse. The calm was always temporary. The stability was always an illusion, hiding the forces building toward catastrophe. The calm center of a tectonic plate, far from any fault line, really is stable. Nothing much happens there. But the boundaries between plates, the fault lines, the subduction zones, those are where the action is. Those are where the accumulated stress gets released in sudden, violent events. If you want to understand earthquakes, you don't study the calm centers of plates, you study the chaotic boundaries where plates interact. This brings me to the deepest insight from fractal geometry, the insight that changes how you should think about stability and chaos. Classical science loves equilibrium, systems at rest, forces balanced, steady states maintained indefinitely. Classical science treats departures from equilibrium as temporary disturbances that the system will correct, but most natural systems don't work that way. Most natural systems are not at equilibrium. They're driven systems, constantly receiving energy from outside, constantly dissipating energy, constantly operating far from any stable resting state. And driven systems don't settle into calm equilibrium. They settle into dynamic states at the edge of chaos. States where small perturbations sometimes die out and sometimes amplify. States where the system is maximally responsive, maximally adaptive, maximally alive. This is called self-organized criticality. Systems naturally evolve toward critical states, toward the boundary between order and chaos, because those states have special properties. Think about a sand pile. You drop grains of sand one at a time. The pile grows. At first, nothing much happens. Grains land, settle, stay put. But eventually, the pile reaches a critical slope. Now, when you drop a grain, it might trigger an avalanche, a small avalanche or a large one. You can't predict which. The system has organized itself to the critical state, to the boundary between stability and collapse. And here's the remarkable thing. The sand pile doesn't stay below the critical slope where everything is calm and predictable. It doesn't push above the critical slope where avalanches happen constantly. It organizes itself right to the edge, right to the boundary, right to the transition zone. This is what natural systems do. They evolve toward criticality. They find the edge between order and chaos, and they stay there, not because anyone designed them to, but because systems at criticality have maximum sensitivity, maximum responsiveness, maximum capacity for complex behavior. Your brain operates at criticality. Neural networks that are too ordered, too calm, can't process information flexibly. Neural networks that are too chaotic can't maintain stable representations. The brain finds the edge between these extremes and operates there. That's why you can think. That's why you can learn. That's why you can respond to novel situations. Your brain is not calm. Your brain is poised at the boundary of chaos, using that sensitivity to process information in ways that stable systems never could. Now, let me tell you why this matters for how you understand the world. When you see something that looks calm, you have two choices. You can assume the calm is real. You can assume the system is genuinely stable, that nothing dramatic will happen, that the future will resemble the past. Or you can ask, is this calm the interior of a stable region, or is it the apparent calm of a system poised at a critical threshold? The difference matters enormously. If the calm is real, if you're in the interior or secure for a stable region, then you can relax. Small perturbations will die out. The system will return to its steady state. The future is predictable. But if the calm is the boundary kind, if you're at a critical threshold, then the calm is deceiving you. Small perturbations might die out, or they might amplify catastrophically. The system might stay calm for years and then suddenly flip to completely different behavior. The future is radically uncertain. And here's the problem. These two kinds of calm look identical on the surface. You can't tell them apart by casual observation. You have to understand the structure of the system. You have to know whether you're in the interior or at the edge. Most people don't do this analysis. They see calm and assume stability. They see the absence of recent catastrophe and assume catastrophe is unlikely. They mistake the current state for the permanent state. This is the trap. Consider how people think about risk. They look at recent history. If nothing bad has happened lately, they assume nothing bad will happen soon. They extrapolate from the calm center of their experience to the chaotic boundaries of possibility. But many systems are not well described by their calm behavior. Many systems spend most of their time in relatively stable states, but occasionally flip to extreme states. The extreme states are rare but enormously consequential. They dominate the long-term behavior even though they're absent from short-term observation. Financial markets do this, earthquakes do this, pandemics do dynamische cities, dynamics, extinctions do political revolutions do this. If you only look at the calm periods, you miss the most important features of the system. You miss the boundaries, you miss the thresholds, you miss the potential for sudden catastrophic change, the geometry of roughness, the mathematics of fractals teaches you to look differently. It teaches you that complexity lives at the boundaries, that the interesting behavior happens at the edges, that smooth, calm surfaces often hide rough, chaotic structures underneath. When I look at a system, I don't ask whether it's currently calm. I ask where the boundaries are, where are the thresholds, where are the transition zones, what would happen if the system moved from the interior to the edge. This is fractal thinking. This is the perspective that decades of studying rough, irregular, complex structures has taught me. The world is not smooth. The world is rough. The world is not stable. The world is poised at countless critical thresholds. I said the world is not calm. The world is filled with boundaries between different behaviors, boundaries that can shift suddenly and catastrophically. Classical thinking sees a stable system occasionally perturbed by external shocks. Fractal thinking sees a critical system constantly generating its own complexity, constantly evolving at the edge of chaos, constantly capable of sudden transformation. The fractal perspective is not pessimistic. It's not about expecting disaster everywhere. It's about understanding where you are in the structure of possible behaviors. It's about knowing whether the calm you see is robust or fragile. It's about being prepared for the boundaries even when you're experiencing the interior. Let me close with what this means for how you should see reality. When you look at a coastline, you're not seeing a simple boundary between land and sea. You're seeing a fractal structure with complexity at every scale. The apparent simplicity is an artifact of your viewing distance. Zoom in and the complexity reveals itself. When you look at a cloud, you're not seeing a simple white puff. You're seeing the visible signature of turbulent processes, chaotic mixing, boundary effects in the atmosphere. The calm appearance hides dynamic complexity. When you look at any system that seems stable, ask yourself, where are the boundaries? Where are the transition zones? What would push this system from the calm interior to the chaotic edge? Because the boundaries are always there. The thresholds are always there. The potential for sudden change is always there. The calm, you see, might be real, or it might be the most dangerous illusion of all. Stability is not the natural state of the universe. Criticality is. Systems evolve toward edges, toward boundaries, toward the transition zones where complexity maximizes and prediction fails. The calm center is the exception. The chaotic boundary is the rule, and the boundary determines everything important about how the system will behave. This is what fractal geometry teaches. This is what the mathematics of roughness reveals. This is why I spent my life studying the irregular, the complex, the rough, because the smooth surfaces are not where the action is. The calm interiors are not where the future gets determined. The stable equilibria are not where nature actually lives. Nature lives at the edge. Nature lives at the boundary. Nature lives in the transition zones where order meets chaos and complexity emerges. Calm is a trap because it makes you think you understand. It makes you think you're safe. It makes you think the future will resemble the past. But if you're at a boundary, if you're near a threshold, if you're poised at the edge of chaos, then the calm is lying to you. The stability is temporary. The safety is an illusion. The only way to avoid the trap is to understand where you are. Interior or edge, robust stability or critical threshold, real calm or the dangerous quiet before the storm. Fractal geometry gives you the tools to ask these questions. The mathematics of roughness gives you the language to describe what you find. The science of complexity gives you the concepts to understand why boundaries matter more than centers. The world is rough. The world is critical. The world is poised at edges. And knowing that, seeing that, understanding that is the beginning of real knowledge, not the comfortable knowledge of smooth approximations, not the false confidence of assumed stability, but the true knowledge of how complex systems actually behave. The boundary never stops generating complexity. The edge never stops producing surprises. The transition zones never stop mattering more than the calm centers. That's the truth fractal geometry reveals. That's why calm is a trap. That's why the most important features of reality live at the boundaries, not the interiors, not comfort, not stability. Truth